Hello students, in this video I'm gonna solve the previous year's questions papers of AHS final examination physics under Assam Higher Secondary Educational Council. So what is the second chapter of physics, that is electrostatic potential and capacitance. Okay, so here I have the previous year's questions papers, Xerox copies of previous year's question papers. I have 24, 23 and 22 as well. So let's see what were the questions asked in these years. Okay, let me take the question paper of 2024 first. So before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you. So now let's start. And if you want to follow me on Insta, then this is my Insta ID, OJHALAKHYAJIT 123. This is my Insta ID. You can follow me on Insta. So now, okay, so what is the question? First question asked in 2024 from this chapter. So let me read the question. Inside a conductor, electrostatic field is zero. Explain. Inside a conductor, so this question is inside a conductor, electrostatic field is zero. Explain. So we need to explain this. Okay, so inside a conductor, electrostatic field is zero. So here we need the explanation. So we know in case of conductor, the electric charges reside on the on the outer surface of the conductor. Suppose we have a metallic block, or metals are conductor, right? So if you suppose it has Q charge on it, then all the charges will reside on this surface, okay, of this conductor. So that's why electric field inside this will be zero. So that's why what we can write, our answer will be something like this. So answer will be, so in case of a conductor, in case of a conductor, the entire charge will reside so instead of writing will reside, let me write reside. In case of a conductor, the entire charge reside on the surface of on the outer surface. Let me write on the outer surface, on the outer surface. So the electric field inside the conductor, is zero. So this is not enough for 2 marks. So what we can do here, suppose we have considered, so let us suppose we have a sphere, suppose uniformly charged sphere, and charge on it, suppose Q, okay, and its radius be suppose capital R, and we have a point inside it. Suppose this is a point P inside it, and radius and distance from the center is suppose smaller, and let us draw the Gaussian surface. Okay, let us draw the Gaussian surface, spherical Gaussian surface through the point P, and radius of this Gaussian surface is suppose r. Okay, so now you see what we're gonna have here. So let me write here, suppose we have a uniformly charged sphere with charge q, with charge q on it, and capital R be the radius of the sphere. P is a point inside the sphere at a distance small r from the center of the sphere from the center of the sphere, right? Let me check, you can see the blue color or not. Yes, okay, it's visible, right? Okay, so now you see let me write the remaining parts here. Okay, because I have not enough space here, so let me write here. Let me clean this question. Okay. So now you see, you continue from here. Okay, so I am writing here. Suppose R with a radius of the Gaussian surface through P. Okay, then according to Gauss law, we know flux. We know that the electric flux through a surface is given by surface integral E dot ds. We know these things, and according to Gauss law, we know that this flux is 1 by epsilon naught times of charge enclosed by the Gaussian surface, right? Charge enclosed by a Gaussian surface. So now you see, in this case, the area of this surface, this Gaussian surface, you see, of radius is small r, that's gonna be the constant here, and if you integrate ds, then that's gonna give you 4 pi r square. Okay, and charge enclosed by this conductor is equal to 0, because since charge inside the conductor, or you can write this, that entire charge, since the entire charge reside on the outer surface, so Q is equal to 0. So Q is equal to 0. If Q is equal to 0, then what we can write? We can write that here this 0 by epsilon naught, that's going to be 0. Then 0 divided by 4 pi r square, that's going to be 0. So here we're going to get electric field is 0 in this case. Okay, electric field is 0. So you have to start the answer from here. Then you see, so I have written this remaining part here as I have not enough space here. Okay, so pause the video and note it. So let me clean this. Okay, hope you can understand this. So what is the next question? So let me check the question paper. Okay, just give me a minute. So where is the question paper? Okay, this one. So now you see, we have another question. So that first one that we have answered, or you need to solve this numerical. The numerical is a 12 picofarad capacitor is connected to a 50 volt battery. Okay, how much electrostatic energy is stored in the capacitor, So that's what we need to answer. Now you see, energy stored in a capacitor, we know that is given by, energy stored in a capacitor is given by U is equal to half CV square, and also it is given by half Q into V. Okay, it is also given by Q into V, and it is also given by Q square by C. Okay, Q square by C, right? Sorry, not Q square. Okay, sorry, not Q. Just give me a second. So if we put here, C is equal to Q by V, then V will be equal to, okay, Q by C. Yes, Q square by C. So this is another expression. Okay, this is another expression. Now you see, so which formula that we're going to use in this question? So we have capacitance of the capacitor and we have the potential difference across it. Okay, so what we have capacitance here. Let me solve this. Here we have capacitance, that is 12 picofarad. So that can be written as 12 into 10 to the power minus 12 farad, right? And we have potential difference, that is 50 volt, right? So therefore here we have C and V. So we're going to use this formula, this first expression we're going to use. Therefore energy is stored in the capacitor. Therefore the energy is stored in the capacitor that will be given by, here's the black one, okay, U is equal to half C V square, that will be equal to half C is here 10 into 12 into 10 to the power minus 12, and potential difference is 50. So this much joule. So here 2 cancels 12, that's going to be 6. So 6 into 50, so that's going to be 300 into 10 to the power minus 12. So if we write this in standard form, then it's going to be 3 into 10 to the power minus 10 joule, right? So that is the energy stored in this capacitor. So hope you have understood this. So let me take another question. Just let me clean this board. Let me pause the video. Here is the next question. If n capacitors having capacitance, having capacitance C1, C2 dot Cn are connected in parallel, so that the total capacity of the combination is given by this expression. So what does it mean? It means C is equal to summation Ci from 1 to n. What does it mean? It means C1 plus C2 plus dot plus Cn. So this question is asked was asked in 2024 as well as I think 2022 also, in 2022 also. Okay, so now just pause the video and note the question. Let me clean this board. Okay, so now you see how to prove this. Okay, just let me clean this board. Okay, give me a second. Almost done, right? So suppose we have n capacitors, connected in parallel, we have n capacitors connected in parallel. So this is capacitance of C1, C2 and Cn. Okay, these are all connected in parallel with a battery of, suppose, V volt. We have considered with a battery of V volt. So that means we have applied potential difference across the across all these parallel combination, be it suppose V, and suppose charge flows out from this V volt battery is suppose Q charge is flows out, suppose. So let me consider that way. Then charge is stored by these capacitors, be suppose Q1, Q2 and so on up to Qn. Okay, let me consider that way. Okay, so here what we're gonna write that okay, so n capacitors how to start? So n capacitors, instead of write that, let me write, suppose V the potential, difference across the combination of n capacitors of capacities C1 comma C2 comma C3 comma dot 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 Cn connected in parallel, okay, and Q1 comma Q2 dot 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 Qn be the charges stored by the capacitors respectively. Right? Okay. So let me consider that Q. So we can write total charge stored, total charge stored. We can write total charge stored, that we can write Q is equal to Q1 plus Q2 plus dot 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 plus Qn. So that means what? You see, if Q total amount of Q charge is flows out from this battery, suppose, and charge stored in this capacitor is Q1, here it is Q2, then here it is Qn, then this total amount of charge that flows out from the battery will be obtained by adding all the individual charges, all the charges stored by individual capacitor. Okay, so we know that the capacitor of a capacitance C is equal to Q by V. C is equal to Q by V, right? So that's why what we can write, that Q is equal to C into V. Okay, Q is equal to C into V. So this is equation number 1 and this is equation number 2. So here suppose C is the equivalent capacitance. Suppose C is the equivalent, or you can say total capacity, or you can say total capacity, or equivalent capacitance, or equivalent capacitance. Okay, now you see, if Q is equal to C into V, then we can write Q1 is equal to C1 into V, Q2 is equal to C2 into V, and similarly Qn is equal to Cn into V. So let me write all these equations as equation number 2. So using 2 in 1. So now you see, pause the video and note these things. Let me clean this part because I have not enough space here on this board. So let me clean this. Just pause the video and note these things. Okay. Now let me clean this. Okay. Now you see, if we use these relations, Q is equal to C into V and Q1, Q2, Qn, this here, then what we're gonna get? Okay, what we're gonna write, using 2 in 1, what we're gonna have, C into V is equal to C1V plus C2V plus dot 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 plus, so here I is this one, plus dot 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 C and V. Now remember one thing, so when you connect this in parallel, so then potential, whatever be the potential difference applied, so so potential difference will be same for all these capacitors when they are connected in parallel. Okay, so that's why I'm writing here V, not V. Don't write V1, V2, so on, right? So it will be V1, V2, V3, so on if you connect this in series. Okay, so now what we can do, C into V, here from here you can take V common, or you can divide each and every term by V. Then doing so you're gonna get C1 plus C2 plus C3 plus C3 plus dot 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 plus Cn. Or you can write same expression using summation. C is equal to summation from I is equal to 1 to n Ci. So this is what we needed to prove, right? So hope you have understood this, right? So now let me pause the video and first note this. Okay, pause the video and note this. Let me pause the video and clean this board let me clean this board and let me go to the next question. Okay, so this is our next question. So that this question was asked in 2023. Okay, so that energy stored in a charged capacitor is E is equal to 1 by 2 CV square. C is the capacitance, V is the potential difference across the capacitor. Okay, that's it. So now you see, so let me erase this question. Hope you have written this question. So now, okay, so how to prove this question, this expression for energy stored in a capacitor, parallel plate capacitor. So now you see, suppose we have a parallel plate capacitor. These are the two plates, suppose, of the capacitor, this one and this one. Okay, so and potential difference across them is, suppose, V. V is the potential difference applied across this capacitor. So when it is fully charged, so it is, suppose, Q positive, it is Q negative. Okay, and suppose V is equal to potential difference across a capacitor of capacitance C. Okay, suppose if at any instant charge is stored in the capacitor. That means when it is not fully charged, at any instant during the charging, the amount of charge stored by this capacitor is, suppose, small q. Let me take a small q. Okay, so capacitor be, suppose, small q, so that if small q is stored in the capacitor, then at any instant, so V is equal to, that can be given by Q by C. This is equation number 1. Now you see, okay, so to store very small amount of charge on this plate, in this capacitor, to store very small amount of charge dq, so how much work required to be done to store very small charge dq work required to be done dw that is work done is equal to V into potential difference into charge, right? So So we have stored dq charge, so dw will be equal to v into dq. So to charge it completely, that means to store q charge, okay, to charge the store, or let me write let q be the charge stored when the capacitor is completely charged. So total work done will be given by total work done W will be given by integrating, that will be obtained by integrating this. So if you integrate this dW, that means integrating V dq, so we have to charge it from 0 charge to q charge. Total charge is q, right? And V is equal to this one, V is equal to q by c. So using equation number 1, we can write integration from 0 to q by c dq using equation number 1. So now, so let me clean this upper part. So hope you have written. Just pause the video and note these things. So now let me clean this, okay. So now you see what we have got here. W is equal to integration 0 to, this is supposed to be q, and q by c dq. So here what we have done, we have replaced this v by q by c, okay. So in equation number 1, I have already written v is equal to q by c. So now you see, if you integrate 1 by c is here, that's going to be remain constant, so here we're going to get integration 0 to q dq. If you integrate this q, then what you're going to get, you're going to get q square by 2. So we are integrating it from 0 to q. Then if you put the upper and lower limit, then we're going to end up getting w is equal to half capital Q square by c, because when you put this upper limit, then you're going to get this. When you put 0, then you're going to get 0. This minus 0, that will be this one, okay. So this work done will be stored as a potential energy in this capacitor. So what, so hope you have written this, okay. So this work done will be stored as potential energy in the capacitor. That is U is equal to half Q square by C, and again we know that V is equal to C is equal to Q by V, right? C is equal to Q by V, and so we can replace Q by C into V, okay. So that's why if you replace this Q square by this expression, then what you're going to get, U is equal to half So C square by V square by C square, sorry, not C square, only C, since Q is equal to C into V, so C square cancels, so we're gonna get U is equal to, so C square cancels, so here we're gonna get half C V square. So instead of writing U in the question, they have written E. Okay, so let me use here E. So here E represents energy. Instead of U, they are using symbol E. Okay, E doesn't mean here in this case, in this particular case that mentioned in the question, this E is equal to half of CV square. So E means energy here, not electric field. Okay, remember this. So this is the expression that we needed to show. So hope you have understood this. So now let's move on to next question. Okay, just let me pause the video. So here is the next question. What do you understand by capacitance of a capacitor? Well, that means we need to define capacitance. Okay, write the relation between picofarad and farad and picofarad, and obtain the expression for capacity of a parallel plate air capacitor. That means between the capacitor plates there is air. Okay, no any other medium, so there is air, and dielectric constant, the value of dielectric constant for air is approximately equal to 1, which is almost equal to vacuum, right? So that's why we are not going to consider any dielectric medium between the plates while deriving this expression for parallel plate capacitor, air capacitor. So do you think that dielectric has important effects on capacity of the condenser? Yes, that's yes. When you insert a dielectric medium without leaving any gap between the plates, okay, if the dielectric constant of that medium is K, then the capacitance becomes K times the initial capacitance. Okay, so now let me clean this board and let me answer these questions. Okay, just let me pause the video for a second. Just so first let me write what do you mean by what do you understand by capacitance of a capacitor. So capacitance of a capacitor, so as I have cleaned this question, so that's why I have to hold this question paper. So what do you understand by the by capacitance of a capacitor? Write the relation between farad and picofarad. So capacitance of a capacitor, capacitance of a capacitor sorry. So capacitance of a capacitor is the ability to store charge when a potential difference, so let me use the symbol Q here. Okay, store charge when a potential difference, suppose B, is applied across the capacitor. That means mathematically the expression capacitance it is given by C is equal to Q by V. Okay, C is equal to Q by V. So next part of the question, write the relation between farad and picofarad. Relation between farad and picofarad. Relation between farad and picofarad. So 1 farad is equal to 10 to the power 12 picofarad, which is written as PF, or you can write 1 picofarad is equal to 10 to the power minus 12 farad. Okay, that is the relation. So now let me pause it and just pause the video and note this. Okay, now next part of the question is obtain the expression for capacity of parallel plate air capacitor. Suppose we have a capacitor here. Okay, these are the two parallel plates, okay, of a capacitor. Okay, and charge stored on this capacitor is suppose on this plate is suppose positive Q, here it is negative Q, and area of this capacitor plate is suppose A, and charge density on this plate, the charge density on this plate is suppose sigma. So similarly on this plate also density of negative charge is also sigma, and density of positive charge is also sigma. We have considered that. Okay, so now suppose Q with a charge on the capacitor plates. Okay, on its capacitor plate of area A of a capacitor. Of a parallel plate capacitor. Of a parallel plate capacitor. Okay. And Q, which is given by Q by A, is the surface charge density, or simply let me write charge density. Right, charge density. And the electric field is between these two plates is suppose E. Now you see this electric field between the two plates is given by E is equal to sigma by epsilon naught, where sigma is the permittivity of free space, okay. Now you see, because we know the electric field at a point due to a charged plate is given by sigma by 2 epsilon, you have already got this. So here we have two plates, so this one plus this one, that's going to be sigma by epsilon naught, right? So hope you have understood this. So now you see again, if the separation between the two plates is suppose D is the separation between the two plates, if D is the separation between the two plates, between the two plates, then potential difference between the two plates, then the potential difference between the two plates is given by, V is equal to E into D. V is equal to E into D, because you have got this relation, I think E is equal to minus dV by dr. Dr is the distance here, so that's why dV will be equal to E dr. So if you ignore the minus sign here, so dr is dr is nothing but the separation in this case, okay, and V is the potential difference. So now you see, that is what we have applied here. So now, okay, so what we can do in this case, so this E can be replaced by this expression. Let me take, this is equation number 1, this is equation number 1, suppose. Let me take, this is equation number 1 and use equation number 1 here. Then V will be equal to sigma D by epsilon naught. So using equation number 1, right? So now let me take, this is equation number 2, this is suppose equation number 2. So let me write here. So what we have got, V is equal to sigma D by epsilon naught. This is equation number 2, okay. So we know that capacitance C is equal to given by Q by V, right? Q by V. So if you replace this V by this expression, then what you're gonna have? Then you're gonna have, okay, just give me a second, okay. So then you're gonna have epsilon naught Q by, if you replace this one by this, sigma D. That's what you're gonna have, right? So hope you have understood this. And you see, using 2, let me write here using equation number 2. So hope this corner is visible to you. Yes, okay. So this sigma can be replaced by this expression, because sigma is equal to Q by A. So we can write epsilon naught, or you can write Q is equal to sigma A, or you can write Q, instead of Q you can write sigma A, right? Since sigma is equal to Q by A, right? So here sigma gone, so we have got epsilon A by D. So this is the required expression of capacitance. So this is the required expression. And next part of this question, that last part, here it is asked, do you think that dielectric has important effects on capacity of condenser? So what you need to write, yes, dielectric has important effect on capacity of a capacity of a condenser or capacitor. So that is what, so how to write the answer? If we insert a dielectric medium without leaving any gap between the two plates of a capacitor or condenser, then the capacitance of the condenser becomes K times the initial capacitance. That's what you need to write. So just let me show you how to write. Let me clean this first. Okay. So now you see, so effect of dielectric medium on the capacity or capacitance of a condenser or capacitor. Okay, so now you see, if we put or if we insert before that, if C is the capacitance of the condenser, when no dielectric medium between the plates, then if we insert or if we fill the gap, between the plates, completely with dielectric by a dielectric medium of dielectric constant K, then capacity or capacitance becomes, let me write it, C dash is equal to K times of C. Okay, so that means we can say the dielectric medium between the two plates of a capacitor that increase the ability to store charge, or you can write this also. So from here, what does it mean? That let me clean this part. So simply we can read, we can write here that we can write the dielectric medium between the capacitor plates increase the ability increases the ability of the capacitor to store charge, right? That is the important effect of dielectric medium between the capacitor plate. So hope you have understood this. So here is the next question. Mention at least two factors on which capacity of a capacitor does depend. Okay, define unit of capacitance and find out the dimension of capacitance using the dimension of charge and potential difference. Okay, so first let me answer the first part of this question. Okay, so what mention at least two factors on which capacitance on which capacity of a capacitor depends. Okay, so what are the two factors? Okay, let me write here, just okay, just stay focused. Okay, so factors on which capacity of a capacitor depends. Those factors are, number one, so first one we can write, geometry of this plate, or you can write also depends on area as well. Area of the plates, capacitor plates, you can write area of the capacitor plates. And also depends on the dielectric medium between the two plates. So this is a capacitor, it depends on the area of each plate and the medium between the dielectric medium. What is the value of the dielectric constant of the material between the two plates. You can write value of the dielectric constant of the material between the two plates of the capacitor. So area of the capacitor plates and the value of dielectric constant of the material between the two plates of the capacitor. These are the two factors. And next part of the question is define unit of the capacitance. Okay, unit of the capacitance. So now let me clean this part and let me answer this question. Okay. So unit of the capacitance, unit of capacitance of a capacitor is farad, right? So let me write this as capital farad F. So here it is asked to define. Okay, define this unit of capacitor. Okay, the capacitance of the capacitance of a capacitor is said to be 1 farad if it can store 1 coulomb charge when the potential difference across the capacitor is 1 volt. That is, we can write 1 farad is equal to 1 coulomb divided by 1 volt, right? So that's how we can define the unit of capacitance of a capacitor. So find out the dimension of capacitance using the dimension of charge and potential difference. We know C is equal to Q by V. So therefore, so if you have written this, let me clean this. Okay. Now you see, Right, we need to find the dimension. Okay, so here you can see dimension of capacitance. When we write this inside the square bracket, it represents dimension, right? Dimensional formula of capacitance will be given by dimension of charge and divided by dimension of potential difference. Okay, so now you see, so what is the dimensional formula of charge? So dimensional formula of charge, that is m to the power 0, l to the power 0, t to the power 1 and a to the power, that is dimensional formula of current. As some books use in some books you may find I also instead of a. Okay, so you can either write a or you can use I also for current. Okay, so hope you have understood this. So then you can write m to the power minus 1, the potential difference of this dimensional formula of this potential difference, that is m to the power minus 1, l to the power minus 2, then t to the power minus 3, then a to the power minus 1. Okay, so now if you simplify this, then what you're gonna have, m to the power minus 1, it's supposed to be m to the power plus 1. Okay, m to the power plus 1, then l to the power plus 2, that's supposed to be l to the power plus 2. Okay, and right, okay, l to the power plus 2. So if you simplify this, then what you're going to get, m to the power minus 1, l to the power minus 2, then l to the power, here 1 plus 3, that's minus 3 will be plus 3, so it's going to be t to the power 4, then a to the power 2. This is the dimensional formula of capacitance, right? So hope you have understood this. Right, here is the next question. Okay, what is capacitor? You know that the capacitor of parallel plate air capacitor is this one, which is already we have derived. What will be its new capacitance if series of capacitance series if a material of dielectric constant K is inserted between the two plates, and also calculate the capacitance of the capacitor shown below. Okay, so here we have a capacitor. These are the two plates. Okay, these are the two plates of the capacitor, and here we have two different dielectric medium with dielectric constant K1 and K2. We need to find the equivalent capacitance of this capacitor. Okay, so now you see, first let me clean this board. Okay, and then I'm going to answer this question one by one. Okay, so here you see so what is a capacitor? So what will be the answer of capacitor? So a capacitor is a system of two conductors separated by an insulator which can store charge, okay, that is capacitor. Now you see, we know that capacitance the next part of the question, of a parallel plate AR capacitor is C is equal to epsilon naught A by D. We know that. Okay, so if a material of dielectric constant, DEC means dielectric constant, K is inserted between the plates, then the new capacitance, let me use another marker, then the new capacitance C dash will be K times of the initial capacitance C, so which is going to be equal to C dash. So instead of C, let's put that one, K epsilon naught A divided by D. So that's going to be the capacitance. Okay, now what will be the answer to the last part of the question? So pause the video and note this. Let me clean this board. Okay, now you see, we have to find the capacitance of this capacitor, which is filled with two different dielectric medium with a dielectric constant K1 and K2. So let me take this part as this distance be D1 and this distance be D2. Okay, this distance be suppose D2. Okay, this given figure, the given or the capacitor shown in the given figure can be considered as series combination of two capacitors. Or capacitance C1 and C2. Let me write here C1 and C2. Okay, C1 and C2. So we can consider this like this way. This is one capacitor, this is another capacitor here. Okay, so this is here dielectric medium K1, here dielectric medium K2. Its capacitance is C1, it is C2, and distance between these two plates is D1, distance between these two plates is D2. Okay, we can consider that. So capacitance of the upper part, that C1, that's going to be equal to epsilon naught. So here dielectric constant is K1, so here we're going to put K1. A be the area of the plate of the capacitor. Okay, area of capacitor plate we can say, and here we're going to put D1. Okay, A be the area of capacitor plate. So now MC2 is equal to epsilon naught K2 A by D2, and is in case of series combination, we know that in case of series combination, how to find the equivalent capacitance. So 1 by C, that's going to be equal to 1 by C1 plus 1 by C2, and so which implies C is equal to C1 C2 divided by C1 plus C2, right? So let's put these values here. Then what we're gonna get here. So let me write one more thing here. We have I have taken D1 is equal to D is equal to D1 plus D2, right? let's put the values here. If you multiply C1 and C2, then if you multiply these two, then what you're gonna get? Epsilon naught square, that K1 K2 into A square divided by D1 into D2 divided by D1 into D2, and this whole thing is divided by then C1 plus C2. If you add these two, you can take epsilon naught and A common, right? Epsilon naught and A common, and within bracket we're gonna get K1 by D1 plus K2 by D2, K2 by D2. So here this epsilon cancels epsilon square, A cancels A square, right? So, and if you multiply this denominator with this term, then we're gonna get epsilon naught A K1 K2 divided by K1 D2 plus K2 D1. So this is the capacitance of the capacitor shown in the diagram. So here one more condition is there. Okay, this is the capacitance. This is the capacitance of the capacitor shown in the given figure. Now you see, it is not mentioned that so these are two halves. Okay, that means it is not mentioned that this D1 is equal to D1 and D2 is equal to D by 2 or not. Okay, if it is, then if so just let me write here. If this D1 and D2, right, suppose these two gaps are equal, then D1 and D2 will be equal to D by 2. In that case, so what will be this expression? So what will be this expression here? So in that case we're gonna get C is equal to in that case D1 and D2 both will be D by 2. So then D by 2 will be taken common, so then we get 2 here, 2 epsilon naught A K1 K2 divided by D into K1 plus K2. That's what we're gonna have, right? So hope you have understood this, right? So so that's all for today. Thank you for watching. See you in the next video. Okay, thank you.